Hello. In this lesson, we will take a look at the periodic table and also some periodic trends that are inherent within its structure. The periodic table is broken up into groups and period. The groups being the vertical columns going up and down, 1 through 18, so there's 18 total groups or families as they're sometimes called. So we have the alkali metals group 1, and then we have the noble gases here in group 18 and all the ones in between. Now, the periodic table is also broken up into periods, so these are kind of trends that keep on coming around again. So we have period 1, which is hydrogen through helium, period 2, lithium through neon, and period 3 and 4 and so on. They're just going to be my horizontal rows going from left to right here. So within these periods, we see a number of different trends that keep on happening over and over again. One of these trends is atomic radius. So atomic radius is basically the size of the atom. So if I just zoom out a bit, so if I have an atom, just a simple one, well, the atomic radius is from the nucleus all the way to the outer edge of where the electrons are, so in their orbits or orbitals. So that's the atomic radius. So the periodic table actually shows a very specific trend in regards to atomic radius. So as we move from left to right, the atom actually tends to go from bigger to smaller as I go from left to right in the periodic table. As I go down, it kind of does the opposite. It goes from smaller to much bigger as I move down. Now, there's two very good reasons for this. The reason why it gets smaller as I go from left to right is kind of counterintuitive, because you would expect as you get more protons and more electrons and more neutrons that, well, the atom should get bigger. But as we were measuring the atomic radius, which is just from the nucleus to the outermost electron, what tends to happen is as I add more protons, the charge of the nucleus actually gets stronger. And because the charge gets stronger, it's able to hold those electrons much more tightly towards the nucleus. So as a result, as I get more protons and more electrons, those protons and electrons are actually closer together because the effective nuclear charge between them is that much stronger. So this is due to, and I'm going to just spell it out here, effective nuclear charge. So that's the charge within the nucleus itself, and it's basically the force of attraction between the nucleus and the electrons. Now, when we look down go down the groups, we see that the atomic radius is going to get bigger, and this makes sense because as I go down from hydrogen, lithium, to sodium, and so on, well, we're actually adding a core shell of electrons each time. So each period, we're just adding on another shell of electrons. So it makes sense that as I go down, I'm essentially going to get bigger because I'm adding more shells. So we have a number of electron shells. So as I get more electron shells, the atomic radius is going to get bigger because electrons are going to get further and further away just because, well, we're going to have more and more of them within their shells. So another trend that we might want to look at is going to be the ionic radius. So ionic radius is going to be very similar. It's going to just be similar to the radius of an atom here, but in this case now it's going to be an ion. So an ion, it's going to either lose or gain electrons. And if it loses or gains electrons, well, that's going to change its effective nuclear charge. It's going to change how those electrons are then arranged in the space around it. So it's going to change how they are going to look around and how they're going to be felt around the nucleus. So when we take a look at the ionic radius, so with the ionic radius, we see kind of an opposite effect as we go from left to right. We actually see that because all the elements on the left are going to be more or less metals, when you lose an electron, now you have more of a positive charge than the negative charge of the electrons around them because we've lost an electron. They tend to be actually very small. And as you go from left to right, and we hit the nonmetals, and now they have an extra electron to accommodate, and all those repulsive forces, well, now they're much bigger. We still have the same trend of small to big because of the shells going down, but we have the reverse now with the ionic radius. So this is ionic. The ionic radius, because the nonmetals have to get bigger to accommodate the extra electron, and the metals actually get smaller because they lose that electron and they're positive, and because they're positive they have that much closer hold on their outer shell electrons. Now the last one we're going to do in this video is going to be electronegativity. And electronegativity is the ability of an atom to attract a pair of electrons in a covalent bond to itself. So it's basically how if two atoms are in a tug of war, and they're different, if they're in a tug of war with the electron pair between them in a covalent bond, whichever one is stronger or more electronegative will win. And electronegativity is a Pauling scale, and it goes basically from 0 to 4. And what happens with the electronegativity and its scale, 0 to 4, we see this trend. And the trend shows us that this E-neg, or electronegativity, actually increases as I go from left to right. And that's mainly due to the size of the atoms, but also it has more to do with their ability to attract this electron pair, or how badly do they want this electron pair. We kind of cancel out group 18 for this one because they don't really play any part in electronegativity. But the halogens, group 17, are actually very electronegative. They want those electrons. Now the other trend we see with electronegativity is actually increases as you go up. So kind of the reverse of our radius in that electronegativity goes up. So due to this trend, fluorine here is the most electronegative atom. And this is because it has a high effective nuclear charge, and also because it only needs one more electron to have that full shell. It really wants it. It has a very strong pull. The next two most electronegative atoms will be oxygen and chlorine, and they form very specific bonds with certain types of atoms that we'll get into a little bit later. But we see this electronegativity trend due to the small effective nuclear charges of these three elements. Metals are not very electronegative at all. They don't want electrons predominantly, so they'll generally give them away, so they'll have very low values, whereas the nonmetals will have relatively high values. Hydrogen is in the middle ground, it's about 2. So we see this overall periodic trend, and these trends are mainly as a result of either the effective nuclear charge of the elements, or they're due to the size or the number of shells. And this can cause like different effects like shielding, or like decreasing in that force of attraction between the nucleus and the outermost shells. In the next video we'll take a look at ionization energy and how we can use electronic configuration to explain the kind of odd trends in ionization energy through period 3.